So here we have a long roadmap problem. So provide the missing conditions or products for the roadmap problem below. No reagent box should contain more than 3 steps, but minimal steps are preferred. Be careful of the lettering when entering your answers. So I started off at part B. I drew out all the structures for the names that you're given, because those are all starred molecules that you're expected to know. So I started off with part B because I could get an answer for one of them. Here, this is Lindlar's catalyst. It takes, remember Lindlar's catalyst takes triple bonds to cis alkenes. So that's what I did here. It's terminal, so with propylene it's terminal, so it doesn't really matter if we would have used that, or sodium metal and ammonia, but we know that we get that from a terminal alkyne. So part B, we figured out. Then secondly, I looked at part A. So how do I get acetylene to part B? Well, it's just like chapter 7, adding carbon chains. So I used one equivalent of NaNH2 so that it would only deprotonate one side of the molecule, and put a negative charge on the carbon so that it could add as a nucleophile to this alkyl halide to add the carbon chain. So I added a methyl group on that side. So that's how you get that from here. Then for the next, then I just went on to part C. I drew out again 2,2-dichloropropane, and to get from a triple bond to a geminal gemdiol, we remember use 2 equivalents specifically of HCl. If you were to only add 1 equivalent, you would have just gotten this, which would mess everything up. So you got to make sure not to forget the 2 equivalents, because remember, after the second equivalent of HCl adds again, this is still the Markovnikov position, so the chlorine is going to add onto that position again. So that's part C. And then from part C, I actually skipped all the way to E. So, oh, I'm sorry, I forgot something. So from here to here, there's one. Sorry about that. NaNH2 to CH3Br and 3 NaNH3L. So you could get from here to here just from that. So one equivalent of NaNH2 is going to one equivalent of NaNH2 is going to pull out this hydrogen. You're going to add CH3Br, and you're going to get you're going to add a methyl group right there. So after step 2, you're going to have this. Then when you use sodium metal and ammonia, that takes you to trans double bonds, so that's how you get from there to there. And to get from this vicinal dihalide to the same product, that's where we get part D. You want to show the elimination of that to get a triple bond. Then you'd want to add your extra carbon, because there's only 3 carbons here and you need 4. Then you want to use your sodium metal. So it's almost the same thing. So after step 1, you're left with this, remember? Then step 2, you add your methyl group. And then after step 3, you get this. So we got that one covered. Then the next step, so now we can figure out this part. So you're given meso-2,3-dibromobutane. When you add Br2 and an inert solvent, bromine and bromide add anti to each other. So when they add anti to each other, they give you the meso product. So So that's right there, just to check. So we figured out part D already. Now we can figure out part F. So we want to get from here to here, but only produce this product and no byproducts. And the way to do that is just using ozonolysis. So when you use ozonolysis, you produce two of the same product. So you get acetaldehyde. And make sure it's in two separate steps because you don't want to get a point off on your exam. And then the last one to do is G. To get alkynes to, aldehydes, you need to use SiA2BH and H2O2 and NaOH. That's like a hydroboration type mechanism where you're adding an H and an OH to a triple bond now, a lot like chapter 6, but you're adding it to a triple bond. You get an enol, which tautomerizes to give you acetaldehyde. So this is a pretty big problem, but it's really not as scary as it looks.